and welcome to all of you who are present here for the uh, InSIS webinar, which we have been doing since 2022, I would say almost regularly and successfully. So today we have with us Dr. R. Sunder. He is a research director at BiSS-ITW, and he has had a lot of experience in the aeronautical fatigue. He's going to talk about the history of aircraft structural integrity program and engine structural integrity program and role of fracture mechanics. So ASIP refers to aircraft structural integrity program and NSIP refers to the engine structural integrity program. And to give a brief bio about Dr. Sundar, he holds a MTech and PhD in aeronautical engineering. He has worked on aeronautical fatigue at the National Aerospace Laboratories in Bangalore, as well as at Air Force Research Laboratories at Dayton and at BIS Labs, Bangalore. And he works on the development of a wide variety of test equipment used in research and industry. He is a founding member and past president and office bearer of InSIS. He is a fellow Indian Academy of Sciences and Indian National Academy of Engineering. He occupies the position of research director at BIS division of ITW India. So with this few words of introduction, I'll now request Dr. Sundar to deliver his talk on the the revised title. I think the original title that was sent in the webinar flyer is slightly different from what has been given as a title over here. So with this revised title, he will go ahead and present his talk. Over to you, Dr. Sundar.
Thank you, Raghu. And if the title has seen a small change, it is also based on some exchange with Professor Raghu Prakashi. He asked me a couple of times whether we should be talking about mistakes. But anyway, it's really a pleasure to share this. What I would call not really a hardcore, science lecture that we normally have at our InSIS platform, but rather a story. But a story which I hope will be interesting for those who are in science as well as in engineering. It will be interesting, if not helpful. I'm going to, because it's a story, I'm not going to kind of come with my first slide of content. So let me start straight away with the story. Very, very early in aviation development, it became clear that, diamonds might be forever, but strength of materials is not forever. And when aviation started, when the first aircraft started flying, and then you had this huge spurt in aircraft development. The first time was in World War I, and then a second time in a much bigger scale, World War II. Commercial aviation really took off after that. And a good beginning for this story would be the story of the Martin 202. It was an aircraft that first flew in 1946. Right? And at that time, when commercial aviation took off, the approach of designers, of those who do analysis, strength, design of structures, you really appreciate that aircraft structures are the most demanding in terms of stressing, because they have to be light enough to take off. You can't apply a civil engineering safety factor to an aircraft structure. So it was always a priority of picking up materials of very high strength. So the limit strength was the consideration, and the Martin 202 was built using high strength materials, and it was actually the first aircraft that went into some kind of testing, because why I picked this one was this is the first example where the people who commissioned the aircraft, they said, we're going to check it out. And they flew 150 hours in 10 days. At that time, it was a great achievement, just to make sure that everything is all right. But lo and behold, after this 150 hours of pre-induction testing, on August 29th, 1948, Martin 202 lost its wing in flight. This was not a very good beginning for Northwest Airlines, the airline that later became a huge airline. Those of you who have flown to the US might remember Northwest Airlines. Because until 2000 and I think 3 or 4 or 6, they were the biggest airline in that part of the United States. At headquarters in Minneapolis, now they are part of Delta. They merged with Delta. And it was found that 7075 high strength aluminum alloy was not all that strong when it came to time and stress corrosion cracking. You all remember, I'm sure this is an example that is cited very often about the de Havilland Comet, which was the first jet transport aircraft developed by a company in the United Kingdom that eventually turned out to be a catastrophic experience because it took off with a lot of fanfare. We had the first crash in January 1954, killing everybody due to explosive decompression in flight. Then, Prestige didn't allow the company to stop flying without finding out what went wrong, and another plane crashed. So it followed that there was a fatigue problem with cracking of the fuselage due to the pressure cycles, because it was a flight. It's an aircraft, pressurized aircraft flying at high altitude. So these essentially, involved cracking for 2 different reasons. The first one had to do with stress corrosion. The second one had to do with poor design and fatigue. But I must note over here that if you look at the documents, in the lectures that we hear about the Comet, the discussion is about square windows and how from the corner a fatigue crack would take off. But actually, the catastrophes happened and the testing showed that there was a hatch right above the cockpit, somewhere over there, that used to break up. But that was also a window. It was not one of the passenger windows, which are typically shown in pictures. So these were the lessons that led up to what happened a little later on, and we have in the experience of the U.S. Air Force, which was the largest user of aircraft, not the producer, but customer for aircraft. They had the real true heroes of the background for what forms the foundation for aircraft design today and for all safety critical structures, not only aircraft, in the nuclear industry, in the power industry, even in the wind energy today. We use the same concepts that came down from heroes like this, which I will talk about in this part of the lecture, the B-47 strategic bomber, and then the F-111. So this B-47 was a very important aircraft. About 2,000 of them were built actually, and the aircraft again was used. It used high strength materials in design, and the specific salient feature of this aircraft was that it was the first high-speed swept back wing. You can see the wing swept back like on modern aircraft, very sleek wing that used to see severe fatigue loads because of the flexure of the wing, and the center plane of the wing, which I've shown over here in this region, there would be fractures in flight. And we keep talking about certain aircraft which we consider to be extremely unsafe. But just imagine that on this aircraft, out of the 2,000 that were built, about 200 crashed because it was a strategic air command aircraft carrying nuclear weapons. And some of them actually were shot down over Soviet territory, over North Korea, I think even off China in those years. But those shot down were hardly 5 or 6. But 200 were lost, mainly due to fatigue fractures at this part. But you don't read much about it because it was a kind of a secret, held at that time. Didn't want to discuss too much. But Jack Lincoln, who eventually fathered the aircraft structural integrity program for the Air Force, he noted in his review that this was the aircraft that really gave birth to the Asip program. So in June of 1958, the Air Force accepted a proposal from the Air Force Research Lab at Wright Pack Air Force Base, and within a few months, the program started as a document which carries this number, and it came out with 3 recommendations. So this is where the engineering starts. This is where our story of how we learn to design safety critical structures really starts. The first requirement was you have to restrict fatigue damage in service. He didn't say how you do it, but he said you have to do it, because till then aircraft were never tested for fatigue, and they were only designed for strength. So imagine if you're an engineer and you use ultimate stress all the time, or at best yield stress, and now somebody tells you, you have to use a stress associated with the fatigue process. That becomes, a kind of a intellectual challenge for somebody who has no experience in that. But that was a challenge posed by the first ASIP document. Then the second recommendation was to come up with accurate methods to determine the fatigue life of aircraft. That was another interesting challenge. And the third was to develop methods for both testing and analysis to prevent service fatigue failures. So this was the first suggestion that an aircraft, before allowing it to fly, it has to go through a process of full-scale fatigue testing. And of course, at that time, it was not really clear how you go about it. So this is when really in 1958, you can say, we as aeronautical engineers, as a community, started scratching our heads and started wondering how to build aircraft that will last. Now, the question was, fatigue failure is likely. When is it likely to occur, and with what probability? So from a viewpoint of fatigue design, what are the kind of early lessons that came up? The first lesson was we learned to work with probabilistic aspects of fatigue. So the probabilistic nature of metal fatigue, it reflects the sum effect of scatter in material properties. That is, you test the same specimens cut from the same material and they'll have a different life. Second, it could be deviations in manufacturing, defects introduced during manufacturing. And third, the differences in service conditions. So you have 3 different variables that affect the probability of a fatigue fracture, fatigue failure. So it turns out that, as I've shown over here, if you look at the Weibull distribution for probability of failure of different materials, it turns out that aluminum alloys will have much less scatter in fatigue life than high strength steel. So immediately it turned out that, if you're testing a steel structure, you have to use a different scatter factor by which you have to divide the fatigue life that you obtain in order to tell someone that, he can use the structure for a certain period of time. whereas that factor would be less if it was aluminum alloy. So the material itself has a huge contribution to how what kind of scatter it will be. Just to give you an idea, if you replace all this with composites, the scatter factor, it gets even higher. So for aircraft, for example, typically today, if you build a metal aircraft, you would give 2 lifetimes to be tested to prove that the aircraft would fly safely for a design life. But if you're building it out of composites, if you use the same load spectrum, which we do not, but if you were to use the same load spectrum, you'd have to give a scatter factor of 13 or even 15, which means you're going to keep testing the aircraft much longer than it's going to serve the public. So it's not even practical. To explain this further, let's just look at this probability of occurrence of fatigue failure against hours of service of an aircraft. So if that is the distribution scatter that you get by testing several aircraft, the ratio is about 3 to 1. You have to take a 3 sigma deviation from the mean and tell the user that, for sufficient protection of safety of flight, he cannot use the aircraft beyond this point. He has to discard the aircraft somewhere over here. That is the integral probability of failure integrated from this plot. So you can just imagine what is the price we pay if we use the scattered and fatigue life to assign a service life, safe service life. However, in 1959 itself, they started thinking about introducing these probabilistic aspects in the aircraft design. And they said that, you have to perform a full-scale fatigue test, do the test under conditions equal to the conditions of service, and then divide it by a scatter factor, which will depend on what material it is and so on. And the aircraft developers were now required to develop methods for both fatigue analysis as well as fatigue testing, taking into consideration these aspects. Now, between the time the version 1 of Asip was accepted and not accepted, but enforced to 10 years later, a lot of things happened. And I would say the biggest hero we see now, not by way of a mistake like it was in the design of the B-47 and several other aircraft, but in the form of a solution of a kind of an angel who came to really help things, is the subject of fracture mechanics. So the subject of fracture mechanics really took off around that time, the beginning of the 60s. And to kind of underline the importance of fracture mechanics, you have to make a really serious mistake. And that serious mistake came in the way of the design of the F-111. The F-111 is a supersonic ground attack air superiority aircraft. What is special about this aircraft was that it is a variable geometry aircraft. So it has a wing that can sweep. It's a variable geometry wing. So in accordance with the Asip version 1, it was full-scale fatigue tested. It showed a life of 16,000 hours. They divided it by 4 and said, okay, you can use it for 4,000 hours. Now, very early in service, there were 2 catastrophic failures in the tailplane. But unfortunately, they didn't set alarm bells ringing yet. They were later traced to fatigue crack growth from weld defects in a high-strength steel load-carrying joint in the tailplane. But then came a real jolt in the form of an aircraft that had just 100 hours of service. You can imagine The aircraft came out of the factory. 100 hours of service is hardly 120 flights. The left wing of the aircraft, shown over here, it's separated during a pull-up right over the Air Force Base, Nellis Air Force Base in 1960. And that exposed serious issues with the design, with material selection, with everything, non-destructive inspection. There was a huge kind of issue with that. There were doubts about the entire fleet because this plane uses critical joints which handle the rotation of the wing, the tailplane drive. After all, these are stabilizers, so they can rotate. So the joints and the drives here were all made of high-strength steel with the ultimate strength of 1500 to 1900 MPa. And you had a forging process used to produce them, and these were weldable steels. So all this together made life terrible. And the issue was really traced to the problem of just using high and ultra high strength materials. So you can just see in historically in the before the 50s, it was the attitude of the designer was to use the highest strength material available, and that attitude did not change even after 10 years. The problem with the F-111 was that it had, what you can call as rogue defects. That 100-hour fracture, or catastrophic failure of the wing, was because there was a rogue defect in the weld, which caused early crack growth. And that was compounded by the absence of residual strength estimates. Because fracture toughness, though it was a parameter already well known in the science field, it wasn't, the importance of that was not appreciated enough in the construction of this aircraft. And there was no method available at that time for residual life analysis based on fatigue crack growth. So that was the situation with this aircraft. But out of every lesson, something unique, something special comes out. So I would say fracture mechanics in the aircraft industry really took off with a bang because you needed to know what will be the tolerable defect. You learned about the importance of detecting defects in manufacturing and in inspection in service. And importantly, very importantly, because that's where I have spent my lifetime, you start learning how to compute the life of an aircraft between the time a detectable crack appears to the point when it's going to lead to catastrophic failure. But there was one extremely unique feature that came out of this lesson, out of this mistake. And you have to give due credit to the innovative attitude of our colleagues at the time. And that was that this is the first aircraft which was subject to a unique workaround. What was the workaround? The US Air Force built a special cryogenic hangar. And in that hangar, they decided that the entire fleet of 1,500 aircraft would be put to test for residual strength. So in this cryogenic hangar, they took the temperature down to minus 40 degrees. And then they would apply a proof load. Keep the wing at 56 degree sweep, apply a load corresponding to minus 2.4 G and up to 7.3 G. 7.3 G means 7.3 times the flight weight of the aircraft in tension would be applied. And lo and behold, 11 of the aircraft actually failed the proof test. And this confirmed the criticality of the weld defect on the aircraft. So based on fatigue crack growth analysis for the first time in aeronautical experience, the aircraft was cleared for 1,500 hours of service till the next inspection and proof test. I think this is a very interesting example of even in a terrible situation, how you can come out with some very interesting, innovative solutions. Because it was clear that at minus 40 degrees, brittle fracture holds the roost, and it's going to cause a premature failure. So, this experience really gave birth to a new era starting from the late 60s, which you can call it an era of disruptive growth of fracture mechanics related R&D and development of a variety of standard testing practices, test methods, which are now used across the board. It's from the aerospace altitude of aircraft that all these things have now percolated into industry in various industries as well. And the idea is very simple, that if cracking is inevitable, we have to make the best of it. And how do we make the best of it? We count on the crack as an indicator of condition. And if there is a crack of detectable size, we then look at how long it will take to grow and divide that by a factor of 2 and assign that as the inspection interval. This factor of 2 is not a safety factor. It is a factor which accounts for the fact that you might just miss detecting a crack when it comes for inspection of detectable size. If it is just smaller than that, then you have to provide for 2 inspection periods. So what is the advantage of this? The scatter in fatigue crack growth life, this is the residual crack growth life, the scatter in that is much less than the scatter in fatigue life. And because of that, as long as you assign an inspection period, you're safe. And you can continue to use the structure for as long as it will serve without worrying about the possibility of catastrophic failure. So fatigue cracks, they turned out to be assets in condition monitoring because they serve as a diagnostic parameter, without inserting any special sensors. All you have to know is how to look for these cracks. They serve as diagnostic parameters for structural health monitoring, and they enable a transition from hard maintenance to maintenance on condition. And this made a huge impact on aviation as we know it today. And I'll come back to this later. But importantly, they also involved a lot of work around the world. And I can just show you examples of what happened in the US, because the work really took off in the US because it was part of the aeronautical industry. The stress intensity factor became a key parameter. And the magic about the stress intensity factor is that it's a similitude criterion. So if you compute stress intensity factor in any object, and you can test a specimen from the same object in the lab and understand its properties, you can now extrapolate it to any structure. That was a huge advantage. Enormous work was done in NASA Langley in the US. Here's an aerial view of that area in the lab as it looked in some years ago. The NASA Langley scientists, and amongst them were quite a few from India as well, many of them from the Indian Institute of Science. So they did a lot of work whose results are being used as references today in aircraft design. They came up with studies to confirm that the stress intensity factor is a similitude parameter. You can see here test results from a rivet loaded geometry where stress intensity will come down with crack size. As crack size increases, K will come down. In a center crack, it will keep going up. But if you plot crack growth rate versus K, all the data fall into a single scatter band. It's a huge advantage, which I'll come to once again. They performed a theoretical analysis and proved on testing that if you stiffen panels, and aircraft wings and fuselage is all about stiffened panels. If you stiffen panels in a particular way, you can have the K function controlled in such a way that you can prolong the period of crack propagation. And these features are standard fare in absolutely all aircraft today. The concept of fail safety was given birth to through analysis and practical tests. So this is the concept which is now part of Asip, and that is that when you design critical joints, you provide for multiple load paths. That is, supposing you have a lug with multiple walls like this, and one of them starts cracking, you can hope to pick up that crack at the next inspection while the other one carries the load. So that is a fail-safe design. Whereas this, if a crack is growing in the main element, that becomes a safe life design. You have to make sure that that crack will not grow to detectable proportions before the next inspection, to catastrophic proportions before the next inspection where you can catch it. And ASIP carries criteria, what should be the allowable defect size and what kind of non-destructive equipment you should use to detect the defects of those allowable sizes. At Right Pack, there's a satellite image of the Right Pack Air Force Base. It's a huge facility, and the lab, the Air Force Research Lab, is located over here. And I had the opportunity to work there for a couple of years, and I remember the amount of work that went on high temperature materials, even while I was there, for engines. In short, this work over there at Westinghouse, which gave birth to ASTM E647 and even the fracture standards, and across the world, even in India, that essentially has turned into an industry. I would call it the fracture mechanics industry today, where you have basically four platforms which together deliver solutions that render safety critical structures safe for indefinite usage. One is fracture mechanics, the stress intensity factor, the J integral, that is purely computational. Other is the computational part to compute these parameters for any structure, for any component, for any crack geometry, size and shape, the equipment on which you can generate the properties of both the fracture as well as fatigue crack growth, and the non-destructive inspection technology to be able to detect cracks before they become serious, before they become critical. So this industry serves safe usage of structures around the world, and it came out of the history that I briefly described to you. There are other elements in that history, of course, but I thought I would pick those examples which stand out. Now, today, a lot of industries are moving to composites, and the question is, how do you deal with composites? Composites are a different ballgame altogether, but we don't have a similitude parameter for composites. We don't have a method to track damage growth in composites during a test. In fact, in our company, we developed a scanner with which we can get these plots that you can see over here. Perhaps one day this will be a platform as well. I don't know, but it's going to be important. And because you are able to look at defects and the way they grow, you can also talk about the risk factor in using structures with cracks. So you can look at the statistics of how cracks will be, what's the kind of distribution of cracks you will have in the safety critical structure, and how that distribution will change with service. And you can translate that into risk analysis. That is to say, here is the risk of using this structure, risk of failure, and in the log scale, in a couple of in a million, how many in a million will fail. And then you do an inspection, and after that, your risk drops and it again grows after that. And what you can do to, deal with your management in the organization to take important decisions. So such risk analysis is supported by lab testing, by tear-down inspections of old aircraft, and by service inputs from individual airframe tracking combined with depot-level inspections. The advantage of this approach is that instead of looking at a distribution of fatigue life, you can narrow it down considerably to a distribution of residual fatigue life, which really governs the periodicity of inspections rather than the time when you have to discard the structure. So it's a huge advantage. And using this advantage, you can then look at how you can take into account variation in one important factor today in service, which is the variations in service conditions from aircraft to aircraft. And if you can do that, you can get the distribution of variation in residual fatigue life because of service conditions and take that into account and adjust your inspection periods. So this way, you can considerably increase the economy of operation of an aircraft and of any safety critical structure for that matter. And at the same time, not compromise on the safety aspects. With aircraft, you have a huge advantage, which you don't have with other structures. And that is that each aircraft comes with a flight data recorder that records all the parameters, whether you want it or not, they're all there. All you have to do is extract them, both for the aircraft as well as for the engine. Now let us look at what has happened after that. This is the latest Asip, what the document says. This was created in 1970, and you can see that it covers the entire life cycle of an aircraft from design right up to retirement of the aircraft. And I'm highlighting here elements which allow you to develop digital twins. This was created in 1970. So pretty much up to date. So very briefly on the chronology of evolution of structural integrity program, up to 1950, you had the importance of demonstrating static strain under limit overloads. Then came the first version of Asip, which was grossly inadequate, as you saw. And in the late 60s, 1970, the final version of Asip was adopted, which includes considerations of safe life, damage tolerance, and fail safety. And very importantly, it includes individual airframe tracking to make sure that you're able to look at the health of individual aircraft. In 85, InSIP was adopted, which covers aircraft engines, and also the fail safety considerations for engines, which is a very important factor because engines are actually flying bombs. They're very high pressure. Today's jet engines, the compression takes the pressure right, beyond 40 atmospheres pressure. So you can imagine at high temperature, 40 to 60 atmospheres of pressure can be a flying bomb. Now, what are the things that allowed all this to happen? On the theoretical side, you have definitely first place goes to finite element method, which solves a lot of issues, and the development of methods to compute residual strength and residual life of structures with defects under service loading conditions. And we can't underestimate the importance of the experimental resources that are required and which are there. That is the development of test systems. Our company, my own career was built in the last several decades on this area. The generation of mill handbook database, which is only possible from experimental data. The development of test technology, which can basically reproduce service conditions. We can say now that in a full-scale fatigue test, if you if you can just imagine the aircraft had a mind of its own, it would think that it's flying because it will see practically load by load all the loads that it sees from takeoff to landing and from flight to flight. And you have digital flight recorders today. You have very good equipment for non-digital evaluation, which got a huge boost thanks to this industry. Now, briefly about the engine structural integrity program. It has the same structure as the Asip, but the important difference here is the focus on the low cycle and high cycle fatigue approaches to fatigue life of engines because they are rotaries. So, because they rotate at, thousands from a few thousand to a couple of 10,000 RPMs of rotation. And if there's one load cycle in each of these due to some reason, you have a huge cycle count, unlike an airframe. So that's, in spite of that, there are huge demands on the life of engines. You can see here for transport aircraft, it's quite huge. And at the same time, there's a huge demand on the defect sides. In aero engines, you do not allow defects even as small as these, which means you need to have, on the one hand, non-destructive equipment which can handle the detection with almost 100% probability of detecting them. Very small defects because they can grow rapidly. Engines are very highly stressed. Their safety factors are even less than airframes. And you need to look at the non-destructive inspection as well as the threshold stress intensity and fatigue limit considerations, which are not the only parameters in airframe design, but here they become extremely critical. And very importantly, both are sensitive to applied stress ratio. This has a particular connotation to us as a community in India, and I'll come to that in a moment. The InSIP document, it specifies how to calculate permissible and detectable defect size. And you can see there are two important parameters here. One is threshold stress intensity range, and the other is the endurance limit. And there is a very complicated process, convoluted process to determine how fatigue limit varies with mean stress or with applied stress ratio. But in engineering practice, there is no method, no standard method to characterize threshold stress intensity range as a function of applied stress ratio for initial defects. This is very important because initial defects, they don't see the same conditions as cracks which are grown in experiments to find out threshold. In lab experiments with long cracks, you get a very different threshold. And I'm delighted to share with you today, some of you who may not be aware, that InSIS is carrying out an interlaboratory study right now, and we hope to finish it this year, to come up with a new testing practice, new test method that characterizes threshold stress intensity as a function of applied stress ratio. We have results already on a naval steel, which we got from DMRL, and a number of Indian institutions have got together along with colleagues in Russia. And we hope to come out with results that will convince the American Society for Testing and Materials to adopt this new method as standard practice. So we hope to have a made in India test method that will be used globally, and that will have a huge impact on the determination of permissible detectable defect size. So the target is to close this work this year. So perhaps Raghu Prakash can set up a seminar sometime towards the end of this year or sometime next year where we can all look at what was achieved. Now, even though Asip and NSIP have already, they're in practice, they're in use, there are lessons that keep coming up. And one terrible lesson that we learned in back in 1989 was the case of the Sioux City crash landing of an aircraft, where the engine practically exploded. But then, as Murphy's Law should have it, the tail engine exploded and messed up the controls of the tailplane. And the pilots had to practically try and land the aircraft using just these two engines to maneuver the aircraft. Half the passengers died, but half survived, surprisingly. The aircraft landed at a speed of about 450 kilometers per hour. So you can imagine the consequences. And that failure was traced to a small 25 micron defect in the titanium disc. So the consequence of that was triple vacuum refinement of casting. Today, we don't have those defects anymore. And the introduction of a fail safety requirement of containment. So today, you cannot develop an engine if you cannot demonstrate that when something breaks inside, the engine will not explode. So that's the fail safety requirement for engines came from this, in part from this problem. And of course, many of you would have seen this picture of the Aloha Airlines Boeing 737 that lost part of its top fuselage in high altitude due to explosive decompression. And that's when we understood the importance of what is called as multi-site damage, where a fatigue crack can simultaneously take off from multiple points. When you do analysis of fatigue cracks for a structure, you only look at one crack. But here you had a string of these cracks, which basically, they strung together and caused a catastrophic failure. But I look at this as an optimist. I'm an eternal optimist. I look at this also as a sign of fail safety. After all, the aircraft landed. Can you imagine now looking at this picture? Whether how great it was that all the controls for the aircraft went through the floor and not through the roof. Because if they had gone through the roof, this was definitely going to crash. And the structure had sufficient residual strength to withstand the impact load of landing, in spite of having lost this part of the aircraft. And there are other situations where, during inspection, a crack was missed out. And as a consequence, you see this particular blade here flew out. And as Murphy's law should have it, it went and penetrated the window of the aircraft and killed the passenger sitting next to the window. That would not have happened if that defect had been seen at the previous inspection. And there are issues like this, where the turbofan disc, practically is shattered. Unfortunately, the engine basically lost its turbofan, but fortunately, it didn't cause catastrophic failure. And fortunately, none of these blades went into the fuselage to cause explosive decompression that could have been catastrophic. The issue here is, we are dealing with very high stresses. We are dealing with good materials. We're dealing with very sophisticated method for analysis and for testing. And I think the message that I would take from this is that we have to get more and more aware of the basics and reinforce those foundations so as not to repeat mistakes that happen. That is the most important thing when there's something terrible like this happens. And for the Asip program, the US Air Force is probably the only agency in the world which organizes annual conferences where scientists and practicing engineers come and share their experience. Every year, they've been doing this every year ever since the Asip program was adopted by the US Air Force. And I think this is an example of how scientists and practicing engineers can collaborate to really improve the quality of what the industry comes out with. And this is a lesson for us as well. And I'm kind of a little disappointed that even though we operate one of the largest Air Force fleets in the world, we don't have that kind of activism in this field, which would give a huge opportunity for academic institutions to get involved with research, which is of practical importance, on which they can get good funding, as long as we can convince the Air Force that it's worth investing on these things. But let us, look at the positive side. Look at the aircraft like the 747. It's probably one of the first aircraft that benefited from the knowledge that came from fracture mechanics of the 60s. Now, would you believe that this aircraft does more miles on the ground over its service life than most of us do on our cars before we sell the car? or discard the car. It does 240,000 kilometers. This is my estimate based on the kind of service life many of these aircraft have. And if it were to fly around the equator, it could do 2,500 orbits and still keep flying. So that tells you how reliable the aircraft are. I fly very often, and I can tell you, a thought never crosses my mind about how old an aircraft is because I know that it's safe. Engines too are getting more and more reliable, and even I, as an aero engineer, find it difficult to believe that the specification today is for a top-notch engine to serve for 10,000 hours. That's 2 years of usage between inspections. It's amazing. And the kind of knowledge that has been accumulated, the experience, it's there for us to see. It's so reliable now, the engines, that for flights across oceans, you don't need 4 engines on an aircraft or 3 engines. 2 engines are good enough, and they're considered reliable enough to carry you across the Pacific or the Atlantic Ocean. Our own aircraft development programs have also benefited from these inputs, and here is a slide which I took from my colleague Vijay Raju from his presentation at a different meeting, where he described the measures for structural health monitoring on the light combat aircraft. So we are also there. With that, I hope I haven't been too much of a bore for some of you. If you have any questions or comments, I would enjoy listening to them. Thank you.
Thank you, Dr. Sunder, for this talk. And now I invite the audience to come up with their questions in the chat box.
Sunder, just a quick question to get it going.
Sure, yeah.
I lost my connection briefly. So you were saying something about the square and the round windows on the Comet. Are you saying that that was not an issue, or it was an issue? I missed that part.
It was an issue, but it was not the fuselage windows were not the main culprit. The main culprit was a hatch on the cockpit.
Okay.
But it was also a window problem.
Right. Okay. Thank you.
Okay, there's a question about how much of a reduction in testing have you seen over the years? I'm sorry to tell you, to disappoint you, but I'm very happy to note that the amount of testing has actually increased. It has not decreased. And the question is, a lot of testing has now kind of come down to component level testing. The idea is that, in an aircraft program, if you have an unexpected failure during a full-scale fatigue test, your entire development program is set back sometime by years. To cut that down, what you want to do is you want to perform as much testing at the component level as possible. This is not to avoid a full-scale fatigue test, but to practically push the probability of a failure during a full-scale fatigue test towards 0, so that you can get a sign-off from the certification authorities who will otherwise not allow you to fly the aircraft. In the aircraft industry, if it's a manned aircraft, you cannot fly it without testing. And in case you're not an aero engineer, you may not know that today all aircraft have to be tested without in any way reducing the load levels or increasing the load levels from what are expected to be seen in service. You have to reproduce the loads exactly as they are. There are some exceptions now being made for composites just to cut down the test time. But for metal frames, there is no compromise on that. So you have to test to 2 lifetimes. If your service life, your design service life is, let us say, 30,000 hours, you have to test for 60,000 hours.
Well, there's one question from Debla.
The next question is on how far. It's a very good question, and I don't think I have a good answer for it. How far do we understand the long service fatigue properties of composites, 80% of which is used in the body of a 787 Dreamliner in comparison to metal structures? I don't consider myself very knowledgeable about composite structures, but I can make two comments on this. The first comment is that composite structures in the aircraft industry today are not stressed to the same level as metallic structures. That is, when I build an aircraft with metal structures, I push the stress levels to much higher levels than I would in a composite structure. So composite structures, the confidence level is not sufficient to stress them. So as a result, actually composite structures more or less are stressed around the same level as metallic structures, sometimes even less. That is one thing. The other thing is, because of the increased scatter factor in composites, the load spectrum for composites is a kind of a corrupted spectrum. It's not this actual spectrum that the aircraft is likely to see. So there are two things that are possible. One is they increase the number of the more severe loads without increasing their magnitude. So that itself is plugging in a certain, safety aspect. But your point is well taken, and I think we'll have to wait and see. Thus far, no big surprises.
Okay, Dr. Sunder, I have some questions to ask.
Sure.
See, in the beginning, you talked about probability of occurrence in one of your graphs.
Yeah.
But what about the probability of detection?
Yeah.
How is it getting integrated in this analysis?
The way the probability of detection is getting incorporated is that the detectable crack size is assigned based on a very high probability of detection. And that's where the probability of detection involvement ends. So your initial defect size, you don't have a distribution in that. Instead, you take the largest size that can be detected with an extremely high degree of probability. That is one thing. And secondly, remember that the computed residual life from detectable size to failure is divided by a factor of 2.
Okay. But again, that's relating to the metal structures.
Right.
That factor 2. Okay.
Yeah.
There is one question before I put the other question.
Yeah, could you
from
please
my side.
comment on corrosion fatigue test being practiced for aerostructural components? Well, this is a little bit of a difficult question for me, because if you look at the mill handbooks for aircraft design, they bluntly state that if a material is prone to corrosion fatigue, don't use it. So when comments like that come, that raises questions about how much of corrosion fatigue testing is done for aircraft. So I would say that not a whole lot of corrosion fatigue testing is done. However, if you look at aero-engine materials, they are being tested, their properties are being generated at elevated temperature. And elevated temperature in aircraft, in nickel-based superalloys, elevated temperature crack growth is not because of creep. Creep is not a problem at those temperatures at which aero-engine, superalloys are operating. Corrosion is the problem. So it's actually the oxidation. That is the issue. So to that extent, you can say that all aero-engine materials are tested for this problem. Why non-destructive techniques are not used widely in detecting crack initiation? Well, see, this is an interesting question, because once you are able to handle the issue of residual fatigue life with a crack, you are no longer worried about crack initiation. If the component is subject to inspection, you assume that you will detect the fatigue crack well before it can cease to be a threat to structural integrity. So the question of worrying about crack initiation doesn't arise. That is why you have inspection periods. However, if you are looking at non-inspectable portions of an aircraft or an engine, what you're talking about will come into play, but in a different way. And there, what comes into play is total fatigue life. And the idea that after that fatigue life, we are going to discard the component, replace it with another one.
Okay,
So
I think well,
crack initiation as a process is of academic interest. It's good to write papers, attend conferences, but from an engineering viewpoint, I'm afraid it's no longer of a great interest. I'm more worried about cracks that I can detect.
okay, I think while others are probably looking at the chat box, I'll ask this question. See, you talked about the regaining of the, what you call, or reducing the risk when you do an inspection and overhaul. Okay. Now, two things happen. One is during a repair overhaul, sometimes there is a cannibalization. That is, you take components from or a part from some other good aircraft, I mean, good component from some other aircraft and use it. So how do these, estimates take into account the remnant life of a cannibalized part and how it interacts with the rest of the system?
That's a very practical question because it is it's experience. There is a mandatory requirement for absolutely all aircraft components that are in circulation. Each one carries its personal file. So today, you can take any component from any aircraft, move it to another aircraft, and the system will handle that transition.
I mean, does it have an intelligent sensor?
No, it's not a question of sensor. These files are they are maintained as part of the database.
Right, but then these are places where the fit and finish will also come into the picture with regard to the local component stress, isn't it? Like let's
Yeah, but
assume that I'm looking for a riveted joint, which is supposedly a snug fit, but actually it turns out it's a loose fit or something like that. Then the stress pattern completely changes.
that's true. But in aircraft assemblies,
Mhm.
first of all, you don't replace small joints. You might replace. You can actually take a wing from one aircraft and put it on another aircraft. The
Right.
tolerances that are maintained are such that everything is interchangeable. All
Mhm.
parts are interchangeable. All engines are interchangeable. Never mind who makes them. They're all
Mhm.
interchangeable. There are very tight standards stipulated for them. But the most important thing, which I mentioned in the beginning, is that you have a record service of every part that's used. You can trace back exactly, the path that it pursued to the point where it's being used.
I mean, that's a good news because it helps to have a digital twin of the aircraft
Oh,
and
yeah,
right? Okay.
absolutely.
Now the other question is, how is the material state or the health being taken into considerations when you do the residual life calculations? No, I mean, if you look at
The
a
calendar life of the material is not a variable used in analysis.
only the fatigue or the mechanical stress cycle is
Yeah,
taken into considerations.
right.
But then, after some usage, I mean, at least with regard to the composites, you will notice that it has a primary, secondary, and tertiary state of damage accumulation, right? So even in metals, to some extent, we can say that you have the loss in strength or the loss in life as a function of the spent life. So how do we kind of bring that in the residual life calculations?
I think this is an issue with composites, mainly because in composites, we are in the same situation with composites as we were with metals before we got involved with fatigue crack growth, where there was a fatigue index, where there was this miners ruled damage summation, which was an abstract number. That number doesn't reflect on damage. It reflects on the fraction of life that you think has been exhausted, because you're dividing n by n, right? So you don't have a picture of the condition of the material. And I'm afraid we are in that condition with regard to composites. But I would again, say that today with composites, the mechanisms, the criticality of different loading conditions is so different from metals that you can't apply the principles that we learned from metals readily to composites today. Just not possible. Doesn't make any sense. For example, we know that metals fail in tension, composites fail in compression, not in tension. We have done experiments which show that the residual strength of a composite actually improves with the delamination if you're doing the test in tension. So I don't know. I would rather confess to my ignorance, inability to address your question in a better way.
No. I mean, I foresee this as an opportunity because
absolutely.
if we had talked about aircraft structural integrity program for the metallic stuff, it's now also the equal impetus to have the similar document for the composites. And I know that there are some people who are working on that, but then, I mean, it hasn't seen the limelight as much as what the Asip for the metallic structures have done. I think there is a question.
Question
or
from Vikram.
comment.
It's a good question on the Aloha incident, which clearly showed that corrosion was involved. The skin on the 737 is corrosion resistant material, but definitely saltwater environment accelerates fatigue crack growth and crack formation and growth in that material. The important thing is that in spite of the fracture, the catastrophic fracture that occurred, duraluminum, as we know it, 2024, is considered to be a corrosion-resistant material. So that's what I had in mind. Even 7075 is an aerospace grade material, which is extremely sensitive to stress corrosion, but it is still used even today in the aircraft industry. So this is not about the corrosion fatigue being discounted as a variable. This is about the approach that's used by designers when they look at these, when they select their designs. In the case of the 737, the problem was not a design issue. It was more an issue of inspection. If the aircraft had been inspected routinely, they would have figured this out without causing the problem that actually occurred. That is what I recall.
So what is the latest in terms of the fatigue meter type of sensors?
The latest today is digital twins, and I'm extremely alarmed by the fact that some of these digital twins do not even incorporate equations of how a crack will grow or a defect will form in the way that we have learned. They use other considerations.
True. I think there was a lot of literature available on MSD and WFD and all those things. I don't know whether they have been brought in as part of the digital twin yet. Okay, so if there are no more questions from the audience, I think I would take the privilege to, on behalf of the Indian Structural Integrity Society, to thank Dr. Sunder for this nice lecture. And maybe if Vikram wants to say a word or two, I think.
No, except maybe if we have a announcement for the next one, if not, we can.
Well, I think next one we are trying to fix with Professor Sanjeev Kumar Acharya from Jadavpur, and he hasn't yet sent me the title, so I'm kind of reminding him on that. And most importantly, for many of them in this group, I think we have the ICF conference that's between June 11th to 16th. So if some of you are attending, then we'll probably be meeting there in person. Otherwise, probably in the next webinar, I can give a dope on what really happened at the ICF. So
Yeah, that'll be nice.
yeah. So with this, I think I will thank you all for having attended this. I could see some known people's names in the list, and thank you, and stay in touch. Stay safe. Thank you very much.
Thank you.
Thank you.
Bye-bye.
Thank you, Sundar.